Welcome to today's episode, where we're diving into the intriguing world of database management systems, or DBMS. These systems play a vital role in managing data across various applications, and grasping their structure and functionality can really boost our ability to work effectively with data. We'll explore the different types of DBMS, their architecture, and the key differences between memory-based and disk-based storage systems. By the end of our conversation, you'll have a clearer picture of how these systems operate and what factors influence their design and implementation. So what exactly is a database management system? At its core, a DBMS is software that helps us create, manipulate, and manage databases. Think of it as the bridge between users and the database itself, ensuring that data is stored, retrieved, and organized in a way that's efficient and effective. There are various ways to classify DBMS based on their purpose, architecture, and the kinds of data they handle. Now let's talk about some of the key components that make up a DBMS architecture. One important piece is the transport subsystem, which is responsible for transmitting data between the database and its users. This component makes sure that when you request data, it's processed quickly and the response is delivered efficiently. Another vital part is the query processor. This component interprets and executes the SQL queries that users submit, optimizing them to enhance performance and ensure that the most relevant data is retrieved. Lastly, we have the execution engine, which carries out the operations specified in those queries, working directly with the storage subsystem to fetch or modify data as needed. Understanding these components gives us a better appreciation of how a DBMS functions as a cohesive unit, ensuring both data integrity and performance. Now let's explore one of the significant distinctions in DBMS: in-memory versus disk-based databases. In-memory databases store data directly in the system's main memory, or RAM. This allows for incredibly fast access and processing, which is particularly useful for applications that need rapid data retrieval and manipulation. However, it's crucial for these systems to have robust durability and recovery mechanisms in place to prevent data loss in case of a power failure or crash. On the other hand, disk-based databases store data on physical disks. While they may not be as speedy as in-memory databases due to the time it takes to read and write data, they offer greater durability and can handle larger datasets. Specialized storage techniques are often employed to optimize their performance and manage data efficiently. Understanding these storage methods helps us weigh the trade-offs when choosing between in-memory and disk-based systems based on specific application needs. When we discuss memory-based databases, we can't overlook the flexibility they provide in terms of data structures and optimizations. When entire datasets fit into memory, like those containing student or customer records, the performance benefits can be substantial. Memory-based databases allow for dynamic data structures, making it easy to adjust and optimize as data requirements change. This adaptability is especially valuable for applications that need to process real-time data or require quick access to frequently updated information. Next, let's take a closer look at how databases are structured, which is fundamental to how data is organized and accessed. Most databases utilize a tabular format made up of rows and columns. Each row represents a unique record in the database, grouping related values identified by unique keys. Meanwhile, each column corresponds to a specific field, representing a single value at the intersection of a row and column. This structure is key to efficient data retrieval and manipulation, helping maintain data integrity and ensuring that relationships between different data points are preserved. We can also classify databases based on their storage methods. Row-oriented systems store data in a traditional tabular format, where each row contains all the fields for a single record. This method is particularly efficient for transactional applications that require quick access to complete records. In contrast, Column-oriented systems organize data by columns, which can enhance performance for analytical queries that aggregate data across many rows. This structure is especially beneficial for data warehousing and business intelligence applications. Some popular examples of row-oriented databases include MySQL and PostgreSQL, while pioneering column-oriented databases like MongoDB and CStore showcase the advantages of this storage method for specific use cases. As we continue to explore the various types of DBMS, it's important to consider the factors that influence their design and implementation. One major factor is data volume. The amount of data being managed can determine whether an in-memory or disk-based system is more suitable. Then there are access patterns. How data is accessed, whether through frequent reads, writes, or complex queries, can significantly impact the choice of database architecture. Performance requirements also play a role. Applications with stringent performance needs may lean toward in-memory databases, while those that prioritize durability might prefer disk-based solutions. Lastly, scalability needs are crucial. As data grows, the ability to scale the database effectively becomes a key consideration. By keeping these factors in mind, developers and organizations can make informed decisions when selecting a DBMS that aligns with their specific goals and objectives. In this episode, we've covered essential aspects of database management systems, including their architecture, the differences between in-memory and disk-based databases, and how data is structured. Understanding these concepts is vital for anyone working with data, whether you're in software development, data analysis, or IT management. As technology continues to evolve, the landscape of DBMS will also change, bringing new opportunities and challenges. By staying informed about these developments, we can better navigate the complexities of data management and harness the power of databases to drive innovation and efficiency in our work. Thanks for joining us today, and we look forward to exploring more fascinating topics in our next episode.